I'm Anil Kumar. In this video, we'll discuss about absolute maximum and minimum, and we'll concentrate when the domain is restricted. So in a restricted domain, we'll always have an absolute maximum and absolute minimum value. That will be our main concentration. Now, this video is being watched on YouTube by students all over the world. However, we follow different algorithms for absolute maximum minimum in different countries, as I've seen from the books. So when I say exceptions to the algorithm, these exceptions may not be exceptions to many students, right? Because the algorithms followed may be different. What I'm using here is the algorithm which is being followed in Canada. Okay. So we'll talk about few terms. First is, of course, absolute maximum and minimum value. Then we'll talk about algorithm, which can help us to find extreme values. They are also called extreme values. And we'll concentrate on restricted domain. And then we'll take exception to this algorithm. I feel that this algorithm is incomplete. We should also include the points where the derivative is undefined. Right? And then I'll take up some examples on absolute functions, since I've seen that many of my students find it difficult to find derivatives of absolute functions. So that's the whole idea. So let's begin with the concept on absolute maximum minimum. This video can be a bit longer, so you can pause in between and then see the rest whenever convenient to you. Now let us take few examples to understand absolute maximum or minimum. So what I'll do here is sketch few graphs. So I'll sketch, let us say 4 graphs here. And then with respect to these, we'll try to understand the concept, okay? So first one, let us have just a straight line, kind of like this. Okay. Then we'll have a parabola. Let us kind of like this. Let's have a cubic function. And let me make an absolute function kind of like this. Okay. So these are common functions. What we notice here is that in a line, there is no maximum minimum, right? There are no turning points. So here we say no turning points. That means no maximum or minimum value. Is it okay? Now here we have one turning point. Let me write one turning point. And that happens to be a local minimum. Now if you see, that is also an absolute minimum. It is absolute minimum because no other value is lower than this value. Do you understand? That is what we mean by absolute minimum, right? Now here in the third graph, you find that there are 2 turning points, and these 2 turning points lead to local maximum and local minimum. When I say local, that means only at this point, around this point value of x, it is maximum. If you go further, kind of here, there is a higher value than shown here, right? So therefore it is local. Similarly, the point here represents local minimum, not the absolute minimum, since this value is even lower than that. But locally, in the same area, in the vicinity of that value of x, it is local. Perfect. Now here we have a corner. Normally, you may say a turning point, but we refer this as a corner. The idea of referring this as a corner is that at this point, f of x is not differentiable. If you try to find derivative at that point, you won't get, right? It does not exist. However, we have a local maximum and which is also absolute maximum. Do you see that? So this is in general we have seen so far without restricting the domain of the function. Now see what happens if I restrict domain. Let us say I say x value is between two values a and b, right? So I'll mark these two values on the graphs. Let us say this is a for me and this is b for me. So those are my restrictions. Now if I restrict a and b, in that case what happens to the function? So that means at x the value of the function is f of a at a, and at b it is f of b. So we are now talking about this much portion of the line. Now here we do have the lowest value and we do have the highest value. Now these two values represent absolute maximum and minimum, right? So I'm representing maximum with letter H, Y value, and minimum with L. Whenever I have restriction on the domain, I will always have absolute maximum as well as absolute minimum. Now look at it. If I use this point as A, and let us say if I use this point as B, in that case we have the lowest value here and the highest value there. Do you see that? So again we have absolute minimum and we also have absolute maximum. Earlier we did not had the absolute maximum, we only had absolute minimum. Perfect. Now in this particular graph, if I restrict my value of a to let us say this value a, right, and I use b as somewhere here, in that case what happens? You will see that at a we are talking about function from here to that point. Now in this case we do have, if this is higher, assume this is higher, so that becomes the highest value. The lowest value, which was a local minimum earlier, became absolute maximum, right? So in all these graphs you notice that we have absolute maximum and minimum values. Similarly here, if I restrict my domain A and B to let us say these points, in that case I do have absolute minimum value L and an absolute maximum value H. So in all these graphs what you notice is that we have absolute minimum and maximum value. So that really means that if we are talking about restricted domain, right? If we are talking about restricted domain, which we also say closed interval. Closed interval like A, B, right? Both included, that is kind of a must. If you're talking about closed interval, then we'll always have absolute maximum and minimum. Now, said that, there is an exception to this. This algorithm doesn't really work if we have a function which is kind of like this. So now let me make some functions here where the criteria fails, which you're talking about. For example, if I have 1 over x, right? So if I have this 1 over x function, and if I take value a somewhere here, for example, and b somewhere there, then we will not have absolute maximum and minimum in the given domain. Reason being, the function is not continuous in this domain. Do you get the idea? So function is not continuous, and therefore we do not have absolute maximum and minimum. So that gives us another condition for having absolute maximum and minimum. So one is a restricted domain, and the second one, which is very important, is function should be continuous. Correct? It should be continuous. If there is a break in between, then we will not have absolute maximum and minimum. Correct? That is very important, right? Now in some books we are referring to functions to be differentiable rather than this, but as you can see there are so many examples. If I have a curve like this, for example, right? Now in this curve, if I restrict my values of A and B, kind of, let us say A and B here, in that case, you do find that we have the lowest value and we do have the highest value. Do you see that? So here the function is not differentiable at the cusp. Function is not differentiable at the corner. Still, we have absolute maximum and minimum with the restriction that x is between A and B. So most important criteria are these two, which is, I'll say 1, restricted domain, and 2, in this domain function is continuous. So function is continuous in the given domain A to B. Okay, with that in mind, we'll now talk about the algorithm which will help us to find, determine, or calculate the absolute maximum minimum values, correct? Now here you can sketch another graph where, let me give that as an exercise, that within this interval A and B, we cannot find absolute extreme values. When we say extreme, we include both maximum and minimum. Is it okay? So you need to sketch a graph so that within this interval, we do not have absolute maximum or minimum value. So that is possible if the function is not continuous. Perfect. Okay. So let's move on and we'll take a few examples and also write down the algorithm which can help us calculate absolute maximum and minimum values. Now the question here is, algorithm for extreme values. We are given a function y equals to 3x over x minus 2. X is between -1 and 3. So let me first develop or write down the algorithm which we figured out just in the last example. Algorithm is that we should have a restricted domain. Right, where both the endpoints are included. Closed interval, we say closed interval. So closed interval is more popular word. Okay, one. Second, this is one thing. Second point is that the function, let's say the function, we'll say function is continuous. Right? That is the second condition. If the function is continuous in the restricted domain, then we are looking at two things. That is, the derivative of the function is 0 or the derivative of the function is undefined. Now in some books, the second condition is not specified. Now when we say undefined, then that really means we have a corner or a cusp kind of a thing. Is it okay? That takes care of radical and absolute functions. 0 is smooth curves, which takes care of turning points. Do you see that? Those are the zeros. So function derivative is 0. It may take a point of inflection also, right? But that may not lead to maximum or minimum value, correct? We'll look into such examples also. Perfect. Now anyway, the last condition here, of course, is you do all that testing. Then if the endpoints are A and B, then you have to just check the values for f of A, right? F of A, then value at B, and the value at all the critical points. So function is continuous, and this, when we are saying derivative is 0 or undefined, we really call them the critical points. So those points are at x equals to c, right? C. There could be many points. So we call them critical points. So at all the critical points, so all the critical points, you have to check values. So let me call this as f of ci, where I is all the critical points. So out of these values, highest value is maximum and the lowest value is minimum, right? So when we talk about absolute maximum, it is highest value. And when we say absolute minimum, it is lowest value. Is it okay? So that becomes the algorithm for us. Okay? We'll talk about it as we move along. Now here we have an example. The example here is y equals to 3x over x minus 2. We have to find whether this function has absolute maximum or absolute minimum in the given domain. It is restricted between -1 and 3. What do we observe here? We observe that at x equals to 2, we have vertical asymptote. Therefore, function is not continuous. This implies absolute maximum or minimum does not exist, which we'll write DNE in future. Perfect. So first test is, in this interval, do we have a continuous function? From -1 to 3, in between comes x equals to 2, and at that point the function is discontinuous, and therefore there will not be any absolute maximum or minimum value. Perfect. So that is how you're going to check it, and at times you may be asked to reason it out. Why? So I think the reason is very clear, right? Let's move on and take more examples. Now we'll apply algorithm for extreme values. Now the function is y equals to x cubed minus 3x squared, and we're talking about interval -1 to 3. So we see that the function is continuous, right? So it makes sense. So that is continuous. Since it is continuous in the given domain, let's find the derivative and let us find the critical numbers. So second step is critical numbers. Which are basically derivatives should be 0 or not defined. So let's find the derivative. It is 3x squared minus 6x. You can factor this taking 3x common. So you get x minus 2. Now here we can say that derivative is equals to 0 for x equals to 0 and for x equals to 2. So we got two critical numbers, and therefore we can say that the critical numbers are x equals to 0 and x equals to 2. The third step is we need to find the value of function at a, the lower limit, at b, the upper limit, and at all the critical numbers, CIs, right? So there could be more than one, right? So let's find these values. So f of a is -1. So let me write -1 here, substitute -1. So -1 cube minus 3 times -1 square, and that gives you, this is -1, and that is -3. So you get -4 here. Find f of 3, which is the other limit. So which is 3 cube minus 3 times 3 square, okay, and that gives you 3 cube is 27 minus 3 cube, this is also 27, that gives you 0. And now we'll find the value of the function at 0 and 2, right? So f of 0 is equals to 0 minus 0, which is 0. And what is the value at 2? F of 2 is 2 cube minus 3 times 2 square, which is 8 minus 4 times 3 is 12, which is -4. Correct? What you notice is that both the critical numbers 0 and 2 are within the interval. Therefore, we are considering, is that okay? So critical numbers are within the interval. So if you compare these values, what do you get? We get the lowest value, which is absolute minimum, and highest value will be called absolute maximum, correct? So if you compare these values, what do you get? So the values to be compared are at the limits 1 and minus 3 and these two critical numbers. Well, we have a lowest value of minus 4 and the highest value of 0 in this interval. Is it okay? So we do see that the absolute value is for minimum minus 4 and for maximum it is equal to 0. However, there are 2 points, right? So the answer will be for absolute minimum we have 2 points which are minus 1 and minus 4, and we have at 2 we again have minus 4, right? As far as absolute maximum is concerned, we have 2 values which are f of 0, right? I mean, I should write 0 and 0, and also at 3, which is 3 and 0. So at times you may get more than one answer as I've written here. Perfect. So I hope that helps. Note that both the critical numbers were within the assigned interval and therefore we compared their values. Perfect. Okay. Let's move on and take the next example. Now here we'll talk about absolute maximum and minimum for the given function f of x equals to 2 times x to the power of 5 over 3 minus 5 times x to the power of 2 over 3 within the interval minus 1 to 2. As you can see, this is a radical function which is continuous in the given interval. Perfect. So first criteria is met, which is it is continuous in the interval minus 1 to 2, both included. That's very important, closed interval. So now we'll look for the derivative of the function, right? So the derivative of the function is 2 times 5 over 3 x to the power of 5 over 3 minus 1, that gives us 2 over 3, minus 5 times 2 over 3 x to the power of 2 over 3 minus 1, which is minus 1 over 3. Now we can actually take 10 over 3 common. Let's take 10 over 3 common. X to the power of minus 1 over 3 also we can take common. We are left with, so when I add 1 over 3 here, I get 3 over 3, which is x, and here we get minus 1, correct? Now this function has 2 critical points. Let me rewrite this. So what we have here is 10 times x minus 1 over 3 times cube root of x. So here we have 2 critical points. Let me call them, sometimes we say critical number and sometimes critical points. When we say critical points, we are referring to both x and y values. When we say critical number, we are referring to the x value. X equals to what? Okay, so here we can see that the derivative is equal to 0 for x equals to 1, and the derivative does not exist for x equals to 0. Do you see that? Now as per our algorithm, both lead to critical numbers, both, not just equals to 0. So that is an exception to rules followed by some books. That's why I'm writing exceptions here. Perfect. So we have all this. Since we have found all these things, that is, we know the function is continuous. Now the idea is, and we have 2 critical points, the idea is that to get the values, and then we can just compare, right? So what is f of minus 1 equals to? Substitute minus 1 here. 2 to the power of minus 1 to the power of 5 over 3 minus 5 to the minus 1 to the power of 2 over 3, right? Now even power is going to make it positive, so we get minus 5 here. The odd power will just keep it negative, so we have negative 2 here. So we have negative 7 as our value. Now let's check 1 and 0, then we'll check 2 also. Okay, so let's check what is 0. So f of 0 is 0 minus 0, which is 0. And then let's check the value at 1. If I write 1 here, I get 2 minus 5, which is minus 3. And if I write 2 here, f of 2, I may have to use calculator now. So we have 2 times 2 to the power of 5 over 3 minus 5 times 2 to the power of 2 over 3, right? So let's use calculator to figure this out. So we have 2 times 2 to the power of 5 divided by 3, okay, bracket close, minus 5 times 2 to the power of 2 over 3, 2 divided by 3, okay. And let's see what this is. It gives me as minus 1.587. Now we have to only calculate the highest and the lowest value, right, to write our answer as absolute maximum or absolute minimum. So let me write like this, absolute maximum. Which is absolute maximum? So we are working with values. F of minus 1 is minus 7, then we have 0. This is negative, this is negative. So 0 is the absolute maximum value, which occurs at 0. So our point is 0, 0, okay? And out of these, which is the absolute minimum value? So absolute minimum value clearly is minus 7, which occurs at minus 1. So at minus 1, we have the value of minus 7. So that becomes the absolute maximum and absolute minimum for the given function, correct? So some of you can sketch the function also to see the result. So it is kind of like this. As you can see, at minus 1, it has a very low value here, which seems to be minus 7, and at 0, it has a maximum value, right? So that is how you could work it out. Is it okay? So 2 will be somewhere here. 2 will be somewhere here. Anyway, so I hope you understand that in algorithm, it is important to include that the derivative does not exist, may also lead to absolute maximum or minimum value, as we have seen in this particular case. Perfect. Now let's take up the next example. Now let me thank some of my subscribers for requesting examples on absolute functions regarding absolute maximum minimum values, right? So that's why I've taken 2 examples actually. Here's the first one. We need to find absolute maximum and minimum for the given function. G of x equals to absolute value of 12x minus x cubed plus 1 in the closed interval minus 1 to 3. We can clearly see this is a continuous function, and let's now sketch this function to understand how to answer such questions, right? Okay, so to sketch, what I will do is that I will actually sketch this part only, right, which is 12x minus x cubed. So we are working on the value 12x minus x cubed. 12x minus x cubed, I could take x common, right? So I get 12 minus x squared, perfect. Now that means that I have a 0 here, and I have 2 other zeros which are at minus and plus square root 12. So let me write down here minus square root 12 and plus square root 12. Is it okay? Now this is a cubic function, as you can see. Leading coefficient is negative. That means right side is going to be up. So if I sketch this function, I am going to get a function which is kind of like this. So we are just seeing the nature of the curve. Is it okay? So that becomes the function, right? Now if I say that I am interested in absolute value of this function, do you understand? Then I have to flip this portion, right? So the function actually becomes kind of like this. So the absolute function will be, let me show it like this. Do you see that? and this value will go like this. Is that okay? Like this. So this remains here as such. I hope you get the idea. So the idea is that the portion within the absolute function actually could be written as a piecewise function, right? So it could be written as a piecewise function where the pieces are being joined together at couple of points. So our points are from minus square root 12 to 0, then 0 to 12 square root, and thereafter. Now we are given this interval minus 1 to 3, right? So we know 3 square is 9, not 12. So 3 will be somewhere here. I'm not sure where, but it will be somewhere here. Minus 1 will be somewhere here. Is that okay? Now, so we have these intervals to work with. So that really means that we are not working with this positive portion. Okay. So we have intervals which are from 0 to minus 1. So let me talk about interval from minus 1 to 0. And then from 0 to 3. Is it okay? 0 to 3. Now in these intervals, what we really see is that the function has been flipped. That means the absolute value, we are talking about its negative value. Do you get the idea, right? In this portion, right? So in this interval, let me redefine my function first to tell you exactly what I'm trying to show. So I could now write down that absolute value of 12x minus x cubed is indeed equal to, in the left portion, we flipped it. So it is negative of this. So it could be written as negative 12x plus x cubed. That is in this interval between minus 1 to 0. Is it okay? You may not include 0 here. You will include 0 on the other side. However, on the right side, it is same as the function itself. It is as 12x minus x cubed if we are talking about interval from 0 to 3. Correct? So our equation g of x can now be written as minus of 12x plus x cubed plus 1. And on the right side, g of x can be written as 12x minus x cubed plus 1. Now that is a very critical step to understand. Take your time and then move forward, right? So in this portion, since we flipped, we are taking negative of this. Here we retain the same function, 12x minus x cubed. So we are writing it as such. Perfect? Okay. Now let's find the derivatives. So derivative on the left side is minus 12 plus 3x squared. And on the right side, it is 12 minus 3x squared. Correct? To find the critical points, what we see is we'll just equate g dash x to 0. So that means that minus 12 plus 3x squared equals to 0. 3x squared equals to 12, or x is equals to plus minus 2, right? Because 12 divided by 3 is 4. Okay. Now let me do that part here also. So we are equating 12 minus 3x squared to 0. So we get 3x squared equals to 12. X squared equals to 12 over 3, which is 4. And x is equals to square root of 4 plus and minus values. So we get plus minus 2. We get the same value. Okay. Now, plus minus 2 is not in this interval. So this plus minus 2 is not in this interval. Is it okay? Therefore, this is discarded, right? So not acceptable. So we'll discard this. Now on this side, we have plus 2. Plus 2 is there. So x equals to plus 2 is valid. Is it okay? That is one thing. Now, what happens at 0? This is very important to understand. As you can see, at 0, there is kind of a switch. I just said we can include 0 on this side. Why not here? So as you can see, it has a negative slope on this side, positive on this side. That means that 0, which is a cusp, it is not defined. Perfect. So what we see here is that we have another critical number here, which is, now let me just use this part of the page and write down critical numbers. I need more space now actually. So we say critical numbers, right? Or points. So what we notice here is that 0 is also a critical number, since at this point the derivative of the function does not exist. Perfect. So it does not exist. So we have two critical numbers. One is 0, the other one is 2, right? So at x equals to 0, derivative does not exist, right? At x equals to 0. So those are the critical numbers. So let us find the value of g of x at all these points. So of course on the limits, which is -1, lower limit. So that gives you, when I substitute -1 here, I get -12, and -1 cube makes it minus, and minus as plus, plus 1, and that gives you a value of 11 plus 1 as 12. Is it okay? Now g of 0 is 0 plus 1, which is 0 plus 1, which is 1, correct? And what is the value at 2? At 2, if I write 2 here, I get absolute value of 24 minus 2 cube is 8 plus 1, and that is, let's do it. So 24, that is 16 plus 1, right? 17. Okay, anyway. So we get these three values. Perfect. And so we can write down our answer that we have the lowest value and the highest value. Perfect. So that becomes the solution of the given question. Correct? So can you write down the answer now? So what is the absolute maximum value? Maximum value is 17 and the minimum value is 1. Do you see that? So that is the answer for the given question. So our answer here is absolute maximum. If they say value, you have to write the value, which is 17, and absolute minimum is 1, correct? If they say at what point it occurs, then you have to write the x value also. Is that clear? So that is an example using absolute functions, and I hope you find it interesting that we did use the point where the derivative did not exist. And that's critical. Otherwise, you lose half of the answer. Perfect? Okay, so there's one more question to go. So let's take next question now. So this is the last example on absolute maximum and minimum. And here you notice that I'm not talking about a constraint on the interval, right? So we have a case where I should write not closed interval. As we initially saw, we could have absolute values of functions even if the interval is not closed, right? So when we do not restrict intervals, we are assuming it's from -infinity to +infinity, correct? The given function is continuous. So let's find the derivative of this function in the given domain. So we need to find derivative of this absolute function. Now how do we do that? That is a big problem. So what we do here is that we first need to redefine the function, correct? The function can be redefined as combination of two bases. It is going to be x plus 2 if x is greater than equal to -2. And it is going to be minus of x minus of 2 if x is less than -2. Now at -2, there is a change, correct? So if you are looking at this function, then you know that at -2, the derivative does not exist, right? So let me make a point here. So we know that h dash at minus 2 does not exist. Is it okay? Now, let us find the derivative at both the points, and then we'll look into it, whether it really exists or not. Okay, I'm rushing to this. I should not. So what I will do here is I'll divide into two intervals. First, let me consider the case when x is less than minus 2, and then we'll consider the case when x is greater than or equal to minus 2, correct? We'll find both derivatives. So the first one here, we can write h of x as equal to x plus 2 whole cube. So the derivative here is 3x plus 2 whole square times 1, right? On this side, I'm sorry, I should have used a negative value, so I'll get a negative answer. Okay. On this side, when x is greater than or equal to minus 2, h of x is positive of this value, which is x plus 2, and that is whole cube, correct? And derivative of this will be 3 times x plus 2 whole square. Now, to find the critical points, we have to equate these to 0, correct? Equating to 0 means here x is equal to minus 2, and in this case also x is equal to minus 2. So that becomes our critical point, and at that point we know the derivative is 0, right? Since we have the same derivative at x equals to minus 2, we do conclude that it does have a derivative at minus 2, right? So it is valid derivative and it is minus 2, right? So we know that it is 0, right? So we know that h prime at minus 2 exists and its value is 0. Because from both the sides we get the same answer. You get the point, correct? Since we get the same answer from both the sides, it does exist and its value is 0, derivative is 0. So that means we have a critical point, right? So our critical number is x equals to minus 2. So let us see what is the value of the function at minus 2. So if I substitute minus 2 here, then we have h of minus 2 equals to minus 2 plus 2 whole cube, which is 0. Is it okay? So that is the function, correct? Now this point, whether it is a maximum or a minimum, we can figure that out by knowing the fact that h of x is an absolute function. So we are taking cube of a positive value. So in this case, range is always greater than or equal to 0, right? So range is greater than or equal to 0 since it's an absolute value cube. So this value becomes the absolute minimum. Does it make sense to you, right? So what we do here is we check the value of the function in close by areas. That is, you check the value at, let us say, we are talking about minus 2. So you can check the value at minus 1. So at minus 1, the value will be minus 1 plus 2 cube will be 1. And at a value which is on the left side, which is minus 3. At minus 3 also the value is 1. Both are lower, right? Both are lower, and therefore we can say that is both are higher, 1 and 1. Both are higher, and so we can say 0 is the least value of this function. And we can conclude that all of the values are higher than this value, and therefore this is absolute minimum value, correct? So that becomes our answer for the given question. So at times you can see that we can also have absolute maximum or a minimum if the interval is not closed, right? We may not have both, but we can have at least one of them in some examples, correct? So that is the example which we have taken at the end. I hope this helps you to understand the basic concept. that if we have a restricted domain and if the function is continuous, in that case, we will have absolute maximum and absolute minimum at either the ends or at a point in between where the function is not differentiable or derivative does not exist, or where the derivative is 0. So with that, we conclude this set of videos. Please feel free to write your comments, share your views, and if you like and subscribe, that'd be great. Thank you and all the best.